brownies, the main property you've got to realize is they're logically unverifiable, which means it's a contradiction. So if you look in the back corner of the room back there, where the ceiling meets the walls, you won't see one because they're logically unverifiable. It means you can't smell them, taste them, touch them, or feel them, but they're there. Right? If we put powder on the floor and we go away and come back tomorrow, you won't see any footprints of the brownies because they're logically unverifiable. Now if we put photographic paper on the wall and we shine ultraviolet light through the room, you won't see any images of the brownies because they're logically unverifiable. And it's a contradiction to assert someday they'll invent a logically unverifiable browniometer that will measure the brownies in the room. Right? It's a contradiction. That's a priori false to make that assertion. But they exist, and they explain everything that's happening in the room. They explain those two people talking about it. One brownie said, "Turn around and say something to her." Another brownie said, "Don't, it's class. You can't do that." But the brownie that said, "Turn around," said, "What up?" Pushed her around. She couldn't help it. You know, "Why'd you do that?" "The brownies made me do it." Right? Nobody can ever accept responsibility for anything because the brownies. Kyle over here, the brownie, you know, wanted him to push his beard like this. And the other brownie said, "No, don't do that." Which one won? You know which one won. Another one said, pushed his hand out. You know, he went back and said, "Wait a minute." So the brownies, you can see the brownies at work by what happens. You people like this theory? Now for those that didn't catch on, I'm not actually advocating this. We don't actually have meetings, you know. People don't actually bother to hold signs anymore. At least not anymore. It's gone on to other things. They fly things onto the White House lawn. You know, they don't pick it. All right. I'm not advocating this theory, but what's wrong with it? Let me tell you this. You are going to see this theory in your college classes. It won't be called this. It'll be called something else. But it'll have the same problem, and I want you to be able to recognize the problem with this theory and be able to see it when you have, I mean, there are many versions of this theory. And you will be presented with them while you're taking, you know, if you stay here for a while at the university, you're going to have some classes where you're going to meet variations of brownie theory. And I want you to be able to raise your hand and say, how does this differ from the theory of unverifiable brownies? And your instructor may say, well, yeah, I took that class from Birnbaum 35 years ago or 42 years ago. I remember that, but I forgot what was wrong with the theory. So you say, well, you should come back and take the class again. What's wrong with this theory? Here's a hint. Oftentimes the answer to a question that an instructor asks is on the board. Not much on the board here. What's this say? Well, remember, we want our explanation to satisfy 5 philosophical criteria that I put up last time. An explanation or scientific theory is deductive. We'll talk about deduction in a bit. And meaningful. That means it's not meaningless. How would you, what are the operationally specifiable empirical tests of the statement? Well, we just decided it's a contradiction to say you can ever measure or detect these brownies in any way, right? You can't look in the corner and see one. You can't smell them. You can't taste them. You can't touch them. You can't feel them. There's no instrument that can see them. Not like a microbe. You can't see them. Germs on your hands without a microscope. But a microscope exists, and then you can see them. You can also detect them in other ways. Now, if I tell you that under this stack of papers, there's a $100 bill, do you know what I'm saying? How would you check it? What does it mean if I say that? Well, what are all the tests that you could do? So the meaning is equivalent to all the tests. If I say there's a $100 bill under here, can you imagine how you would check it? I know what you're thinking. You're thinking, the table is increased in mass by the amount of a $100 bill. So if I push on this and measure, how much it moves, it will move by less than I would expect if the table had no $100 bill, right? Or you could x-ray through here and you might see there's a little thread that's in there that's metallic in the $100 bill. You should be able to see that if you x-ray. Can you think of anything else? I know you thought of those two right away. What else might you do to check it? Pick up the papers. Okay? There. I know what you're saying. You said more than just pick them up. What would you do if you picked them up? Look, right? That's what you were thinking. Pick up the papers and look. That's what she meant. You're going to look for it and see if you can see it. And then if you looked at it and it looked like it might be there, you might ask yourself, maybe I need to turn it over. Maybe it's only printed on one side. Maybe I need to hold it up to the light. Maybe I need to shine ultraviolet light on it, make sure it's the right ink, because it could be a counterfeit. Maybe it's not a $100 bill, but something that looks. So there's a lot of tests you could do. So there's many, many things you could do to check for it. And that's all the meaning. The meaning is equivalent to all the things you could do to test it, to go about testing it. You should be able to see it. You should be able to pick it up and turn it over. You should be able to hold it up to the light. You should be able to check the paper, that it's indeed the right kind of paper for $100. There's a lot of tests you could do. So there's a lot of meaning in that statement. And that meaning is equivalent to all the ways you would go about checking it. Now, if there's nothing you can do to check it, if I tell you, there's 12 logically unverifiable brownies here, how would you check it?
Yeah.
There's no way to check it. Not just that it's hard to check, but in principle you can't check it. If I say there's a bottle cap on the moon, a 7-Up bottle cap on the moon, you might say, boy, it's really hard to check that. You'd have to get a rocket ship. You'd have to fly there. You'd have to search the whole moon, and then you'd find out whether there was or what. That'd be a really big job, wouldn't it, to search the whole moon for a bottle cap. But you understand how you would look. And if you found one, you'd say, wow, he was right. How did he know that? So you can imagine it, right? You can imagine all the tests you would do. You can imagine how it comes out. So you know what I'm saying. But if I say there's a logically unverifiable brownie, or there isn't an unverifiable brownie, or it has fringes or it doesn't, you don't know what I'm saying. I'm not actually saying anything. So you could say it's not even false. And this whole theory, it isn't that this theory is wrong. It's not even wrong. Because it can't be wrong, you can't disprove it. That's what somebody else might come and say if you were an advocate of it. Say, oh yeah, disprove this theory. If it can't be disproved, it's not a theory. Scientific theory is one that can be disproved, and just a good theory, one that can be disproved and just hasn't been yet. People try to disprove it, but they failed to disprove it. They did lots of tests and just failed to disprove it. And it's not even wrong, it's meaningless. It's not saying anything. All right, any questions about that? Now let me tell you about induction and deduction, which are two kinds of arguments. Do you need more time with anything on the board here? So this is the theory of unverifiable brownies. Famous theory. You should know it, but you should know what's wrong with it. It doesn't qualify as a scientific theory. All right, let's talk about induction and deduction. These are two kinds of arguments. And by an argument here, I don't mean, yes, you are. No, I'm not. I don't mean like a quarrel. I mean a reasoned presentation that leads to a conclusion. So you give arguments for or against something. And there is induction and deduction. Let's talk about deduction here first. Here's an example of a deductive argument. This one is attributed to Aristotle around 400 BC. Aristotle said, first premise, piece of one here is the first premise, is that all Athenians, and by Athenians he meant a citizen of Athens, all Athenians are, I'll say Greeks, he would have said Hellenes. So all Athenians are Greeks, and if premise 2 is the case, premise 2 is Socrates is an Athenian, now, if these two premises are true, if it's true that all Athenians are Hellenes or Greeks, and if it's true that Socrates is an Athenian or a citizen of Athens, can you draw any conclusion?
Socrates is Greek.
So we don't need to do anything else to reach a conclusion based on this, right? So here's an argument leading from these premises. If the premises are true, we get to draw the conclusion C that Socrates is a Greek, right? So if the premises are true, so in this case, if both premises are true, let me write it this way. If the conjunction from I equals 1 to n of the piece of I are true, in other words, they're all true, so if all the premises are true, then the conclusion is true. It's guaranteed. What's the principle of logic? And I'll teach you two principles of logic in this class. There's a principle of logic called the transitivity of implication. And it's written in different ways, and I'll write them out for you in here. So the transitivity of implication is the principle you're using right here. Transitivity of subset relation is another way to phrase it. So set theory and logic are intimately related, and I'll give you Cliff Notes version here of this basic principle. We'll have two logical principles. The logical principle is here, transitivity. If A is equal to B and B is equal to C, you know A is equal to C. Any of you see the movie Lincoln that came out a couple years ago? Remember in Lincoln he talked about equality. All two things equal to the same thing or equal to each other. The writer knew that Lincoln liked geometry. Lincoln had always said, he's the guy, remember, walked through the snow to borrow a geometry book and had to do, he was poor, had to do his geometry on the back of a shovel with a piece of coal, born in a log cabin. And he always said, I'll tell you how to learn law, get a geometry book. If you want to understand reasoning and arguing, you need to understand geometry. Because geometry is pure logic. At any rate, so they put into the movie Lincoln, they put in that sentence talking about equality. Two things equal to the same thing or equal to each other. So if A is equal to B, and B is equal to C, that means A is equal to C. So equality is a transitive relation. A equals B, B equals C. Greater than is a transitive relation. If A is greater than B and B is greater than C, you know A is greater than C. And if all A's are B, and all B's are C, you know that all A's are C. And this is the same as saying if A is a subset of B, where this is the subset symbol, and B is a subset of C. Sorry that the C and the subset symbol kind of look alike. The subset symbol kind of looks like a U on its side. That's subset. And the idea of subset means that every member of the set A is a member of the set B, is what that indicates. A is a subset of B. So if A is a subset of B and B is a subset of C, that means that A is a subset of C. It also gets written this way. If A, then B, and if B, then C, means if A, then C. It also gets written this way. A implies B, and B implies C, means A implies C. It also gets written this way. A implies B, and B implies C, means A implies C. Transitivity of implication. When it's written this way or this way, basically this symbol means implies. Sometimes it's this or this indicates implies. Okay, so if A is true, then B is true, is what you're saying when you write it out this way. Everybody clear on that? Mm-hmm. So this is, well, we'll do it with Venn diagrams too, as long as we're at it. Here's a Venn diagram. All A's are B. So every member of the set A is a member of the set B. And all B's are C. So every member of the set B is a member of the set C. That means all A's are C. So if all the A's are included inside the set B, and all the members of set B are included inside the set C, that means all the members of A are members of the set C. And this is called transitivity in general, when it could be equality or greater than or implication. But in this case, it's the transitivity of set inclusion, when it's written this way, people use that phrase, or the transitivity of implication, when it's written this way. I'll write the word transitivity here for you. Transitivity of preference is a question that's an empirical question in psychology. If you prefer A to B and you prefer B to C, does that mean that people would prefer A to C? So this will come up in economics and psychology and what's known as behavioral economics or psychology, and that's there's arguments about whether it's rational to be transitive or not. People have all kind of interesting publications on it. All right. This is an example of deduction. Deduction goes from premises to conclusions using logic. It's kind of in the world of, well, we have definitions and then logical statements, empirical. It's in that logical category. Although the statements might be empirical statements. These are empirical statements, but we're using logic to reach a conclusion. Any questions about that? That's the idea of deduction. This is one deductive principle. Let me teach you another principle of, another logical principle that we use in deductions. Everybody clear on this so far? Can I erase? Let me ask you this. If the conclusion is true, does that mean that the premises are true? If you take two premises, and if you know the conclusion is true, does that mean that the premises are true? If the deduction is logical? Answer, no. Let me give you an example why not. Suppose I say, premise one, all bread is made of cyanide. And premise 2 is everything made of cyanide is good to eat. What's the operational definition of good to eat? If you feed rats with water and something and they'll live, more than half of them live more than 2 weeks, it's good to eat. What could you conclude if these statements are true?
Bread is good to eat.
Is that true?
Yes.
Yeah. So, from false conclusions, you can reach a true conclusion. So, bread is good to eat. So just because you have a true conclusion and you use logic doesn't make the premises true. This is the nature of scientific explanation. It consists of premises from which you can deduce the things to be explained. It's meaningful. Those are the first 2 criteria. Does that mean you can prove your theory is true? No, but in the movies they're always saying, oh, I'm going to prove my theory is true. They doubted me, but I proved it true by eating bread. That bread is made of cyanide and everything made of cyanide. They doubted me, but I ate the bread and I lived, and that proves that bread is made of cyanide and everything made of cyanide is good to eat. You don't prove scientific theory is true. You can't. Because the relationship between a theory and what it's supposed to explain is like between premises and conclusions. The theory consists of a set of statements from which you can deduce things that may or may not be true. So just because a conclusion is true, so we know that if the premises are true, if we can say this, if the premises are true, the conjunction of the premises, then the conclusion is true. But if the conclusion is true, we don't know anything about the premises. Now, if the conclusion is false, do we know anything about the premises? If the conclusion is false, we know at least one of the premises is false. Something's wrong with the explanation. They might both be false, but if the conclusion is false, we know something's wrong with the theory. So you can disprove theories. Here's the logical principle that states that. If A then B is the same as, I will write if and only if. So if A then B is the same as, or is true, if and only if not B, then not A. Well, we can write it this way. A implies B. If and only if, two-headed arrow is if and only if. Sometimes is written IFF, or if and only if, is the same as which means that if this is true, then this is true, and if this is true, then that's true. That's what if and only if means. So if A then B, or A implies B, if and only if not B implies not A, where this thing indicates not. Sometimes people will write B with a little c up here, meaning B complement, meaning everything that's outside the set B. Sometimes they'll write B bar. These are other notations for not B. All right, let's show our Venn diagram to represent that one. So this one represents transitivity of set inclusion. This one right here, or another way to write it let me write it, all A's are B. All A's are B is the same as, I'll write it this way. All not B are not A. Yes, there's another way to write the same thing. So all A's are B means A is a subset of B, or if A then B. Now out here, outside of B, isn't this the world of not B? So this area out here is not B, or not B. Are there any A's out there? No. So you shouldn't find, out there in the world of not B, you shouldn't find any A's. Where's the not A's? They're everything outside of A. So everything in the not B is not A, right? So all the not B's are not A. I can indicate the not A's by the lines that go this way. Everything outside of A, so this is not A, and so out here in the not B's are all not A. All right, everybody clear on that?
What's this principle called again?
What's what?
What's this principle called?
It's basically the definition of what if A then B, or all A's are B means. Yeah, I don't know, maybe there's another name for it. Probably a name in Latin for it. It's escaping me at the moment. All right, but this is the second principle that we have in this class. Let's illustrate it with a quick little check that we understand. And again, I'm going by my clock. That one on the wall is a little bit fast, by a couple minutes. Here's the question about it. We've got 4 cards here. All the cards, you can assume this is true. All the cards have an integer on one side and a letter on the other. And by an integer, I mean a number that's a whole number. It can be expressed by an Arabic number. And on the other side's a letter. We're going to use the Roman letters. So 1 of 26. And the integers, I guess there's an infinite number of integers. So you can assume all cards have a letter on one side and a number on the other side. In other words, we don't have some with a number and a blank, or some with a number and another number. All of them have a number on one side and a letter on the other. Everybody clear on that?
Yes.
So all the cards. Now here's a conjecture. Conjecture is a statement that we put forth like a hypothesis that might be true or might not be true. So here's our conjecture. Conjecture is all cards with an even number on one side have a vowel on the other side. All right, so here's a conjecture. Might be true, might not be true. Remember, a meaning of a statement is equivalent to all the tests that you can do to find out if it's true or not. Started imagining lifting this up to look for $100 bills, see if they're in there. So the question is, what does that statement mean? Do people understand what it means? So the meaning is equivalent to the tests. So the question is, all right, what is the smallest number of cards and which ones? What's the smallest set of cards we have to turn over to check, to test the conjecture? And by test means that if it's false, we'll know it's false. All right, so what's the smallest set of cards to turn over to test the conjecture? And by test, I mean we'll know for sure that it's false if it is false. What do we do? You know what I mean by an even number? I mean -2, -2, -4, 0, 2, 4. Numbers that are divisible by 2 without a remainder. Right? So that's an even number. What do we mean by a vowel?
A, E, I, O, or U.
Yeah, we're not going to get into Eastern European names like sometimes, Y, kinds of things. So we're going to say that a vowel consists, so the even numbers like 2, 4, 6, 8, vowels are going to be A, E, I, O, or U. So everybody clear on that? And the question is, okay, so 0, you don't have to turn any over. You have to turn over only the 1, only the 2, only the A, only the B, or do you have to turn over the 1 and the 2, the 1 and the A, the 1 and the B, the 2 and the A, the 2 and the B, the A and the B, 1, 2, 3, 4, 5, 6, the 1, the 2 and the A, the 1, the 2 and the B, the 2, the A and the B, the 1, the A and the B, 3, or 1, 2, A and B, all 4. There should be 16 possibilities, multiple choice in this case with 16 possibilities. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so there's 16 possibilities as to what this statement means. All cards with an even number on one side have a vowel on the other. Everybody understand what that statement means? Then you understand how to test it, if you understand its meaning. Write down what you think is the right answer. Multiple choice, so you can choose which of these things do you think is the right answer. Okay? I will give you 15 seconds.